In this video, we will be talking about the sp3d and sp3d2 hybridized orbitals. The sp3d hybridized orbitals have 5 different electron groups. So atoms with 5 electron groups around it are a trigonal bipyramidal electron geometry. Some of the possible molecular geometries are seesaw, T-shape, and linear. The angles within the trigonal bipyramidal electron geometry are typically 120 and 90 degree bond angles, where the 90 degrees are between the axial and the equatorial atoms. In order to form an sp3d, you need to mix one s, 3 p's, and a d. So 5 regular orbitals go into the hybridization, and you get 5 hybridized orbitals out. In some instances, atoms like arsenic can use empty d orbitals from its valence shell to enable it to bond 5 times with things like fluorine. So this would be arsenic pentafluoride. The d orbitals are used to make sigma bonds. So you would have with your f orbitals forming these sigma bonds through direct overlap with your arsenic as the central atom. So the sp3d hybridized orbital uses an s, 3 sets of p's, and a d. So you have a total of 5 different regular standard orbitals going in. The remaining 4 d orbitals are left unhybridized. So you will have a total of 5 hybridized orbitals with which to bond, and you will have 4 sets of unhybridized d orbitals. Because you have 5 orbitals that are hybridized, the shape will follow something that has 5 electron groups, which is the trigonal bipyramidal electron geometry. Adding an extra d orbital into the mix gets you an sp3d2 hybridized orbitals. These are used for atoms with 6 electron groups around it, which gives you an octahedral electron geometry. The possible molecular geometries for an sp3d2 would be square pyramidal and square planar, depending on how many valence electron pairs you have. The bond angles are going to be 90 degrees apart. Typically, when an atom is using sp3d2 hybridized orbitals, it is using some of its empty d orbitals from the valence shell to form those hybridized orbitals. An example would be sulfur hexafluoride. Sulfur, which is in the 3rd row of the periodic table, has access to the 3d orbitals. It typically doesn't use them because they are very high in energy. But it can use those d orbitals, 2 of them, to hybridize with its s orbital and 3p orbitals to make a total of 6 hybridized orbitals, allowing it to bond to 6 fluorine atoms. When doing so, it will make sigma bonds with the fluorine, giving you this arrangement here with the sp3d2 hybridized orbitals on the sulfur in the center. In terms of our electron diagrams, we would be mixing a single s, 3 sets of p's, and 2 sets of d's, leaving 3 unhybridized d orbitals. So we're taking a total of 6 standard atomic orbitals, mixing them together to hybridize them, resulting in 6 degenerate, meaning that they have equal energy, 6 degenerate orbitals that are sp3d2 hybridized orbitals. This gives us an octahedral electron geometry, and we have 3 sets of unhybridized d orbitals remaining.